DeepSeek V4 is a major leap for open-weight language models. Two variants: V4 Pro, with 1.6 trillion total parameters, only 49 billion active per token via mixture of experts, and V4 Flash, a leaner 284 billion parameter model with 13 billion active. Both support a full 1 million token context window, trained on 32 trillion tokens. The headline result: a Codeforces rating of 3,206, legendary Grandmaster tier, the highest ever achieved by an AI system. In this video, we'll cover the key innovations: a new hybrid attention architecture, improved residual connections, and a novel post-training method called On-Policy Distillation. Let's get into it. Standard transformer attention scales quadratically with context length. At 4,000 tokens, you have a baseline. At 32,000 tokens, you're at 64 times that cost. At 128,000, over 1,000 times. At 1 million tokens? 500 times the baseline. Computationally infeasible. The KV cache makes things worse. At 1 million tokens, it reaches 8 gigabytes per transformer layer. With 60 plus layers, you need terabytes just for the cache. Prior solutions like sliding window attention or linear attention sacrifice quality for efficiency. DeepSeek V4 takes a different path. Compress the KV cache aggressively, then attend selectively, achieving just 7 to 27% of V3.2's resource usage at 1 million tokens. V4 Pro is the flagship: 1.6 trillion total parameters, 49 billion active, 256 routed experts per layer with 8 active per token. At 1 million tokens, it uses only 27% of V3.2's compute and 10% of its KV cache. V4 Flash is the speed-optimized variant: 284 billion total, 13 billion active, 64 routed experts with 4 active. Even more efficient: 10% of V3.2's compute and 7% of KV memory at 1 million tokens. Both models share the same architecture: multi-head latent attention extended with CSA and HCA, DeepSeek MoE, manifold constrained hyperconnections, and multi-token prediction. The efficiency numbers are what make million-token deployment practically viable. V4 stacks 5 major innovations on a standard transformer. First, attention. Multi-head latent attention extended with CSA and HCA for 1 million token context at a fraction of the usual cost. Second, DeepSeek MoE, 256 experts, only 8 active per token, scaling parameters without proportional compute. Third, MHC, manifold constrained hyperconnections, improves gradient flow by constraining the residual routing matrix to be doubly stochastic. Fourth, multi-token prediction predicts several future tokens per step for a denser training signal. Fifth, the Moron optimizer uses Newton-Schultz orthogonalization for more principled gradient updates than AtomW. These 5 changes make V4 fundamentally different from V3 in both architecture and training. CSA, compressed sparse attention, is central to making 1 million token context work. Here's the flow. Start with N tokens in the KV cache. Step 1. Compress. Every M consecutive tokens are pooled into a single entry via learned aggregation, reducing from N to N over M entries. Step 2. Index. The Lightning indexer scores each compressed entry against the current query and selects the top K most relevant chunks. This is differentiable and runs in sublinear time. Step 3. Attend. Only those K-selected entries participate in attention, global coverage over the entire million token context, but cost proportional only to K. The Lightning indexer's query key path is also trained with FP4 quantization-aware training, making indexing fast and memory efficient at inference time. HCA, heavily compressed attention, complements CSA. Where CSA compresses M tokens to 1 entry, HCA compresses M prime tokens, where M prime is much larger than M. The compressed sequence is short enough that HCA can run full dense attention over all entries, no sparse selection needed. CSA is like a search engine. It finds specific relevant chunks anywhere in the context. HCA is a summary view, a coarse global overview of the entire window. Both are needed. The efficiency results are dramatic. Against DeepSeek V3.2 at 1 million tokens, V4 Pro uses just 27% of flops and 10% of KV cache, a 10 times memory reduction. V4 Flash goes further, 10% of compute and 7% of KV memory, 14 times less memory. This is the difference between million token inference being a research exercise and being deployable. Standard residual connections add x plus f of x. Hyperconnections generalize this with a learned matrix B times x plus f of x. An unconstrained B causes instability. Some gradient directions vanish, others explode. MHC fixes this by constraining B to the Birkhoff polytope, doubly stochastic matrices, where every row and column sums to 1. This ensures residual routing redistributes information between streams without amplifying or losing it. The constraint is enforced during training by the Sinkhorn-Knopp algorithm, which alternately normalizes rows and columns until B satisfies the doubly stochastic property. MHC also expands the residual stream by a factor of 4, creating 4 parallel information pathways that can each specialize better gradient flow throughout the entire network. 4 infrastructure pieces make this scale work. TileLang is a domain-specific language for GPU tile programs, enabling hand-tuned attention and MoE kernels without raw CUDA boilerplate. Mega MoEP is the expert parallel MoE dispatch kernel, achieving 1.5 to 1.9, 6 times speedup by fusing routing, gathering, and computation into a single pass. FP4 quantization-aware training is applied to MoE expert weights and the CSA indexer's query key path, with lossless FP4 to FP8 dequantization at inference. Finally, all critical kernels produce bit-identical outputs regardless of batch size, essential for reproducible distributed training. DSEC, their elastic compute platform, handles fault tolerance and auto-restarts so hardware failures don't derail multi-week training runs. Pre-training spans 32 trillion tokens across a 4-phase context-length curriculum. Phase 1 trains at 4,000 tokens, building core language understanding over the bulk of the data. Phase 2 extends to 32,000 tokens for multi-document reasoning. Phase 3 reaches 128,000 tokens, activating the CSA and HCA paths for the first time. Phase 4 hits the full 1 million token window, using synthetically generated data, requiring genuine long-range reasoning. Throughout all phases, multi-token prediction creates denser training signal by predicting several future tokens per step. And the muon optimizer, with Newton-Schultz orthogonalization, is used from the very first step for all applicable weight matrices, providing more balanced gradient updates than AtomW across the entire run. 2 techniques prevent instability at this scale. First, anticipatory routing. Standard MoE routing uses current step activations to assign experts, creating oscillation. Good experts get overloaded next step. Anticipatory routing uses historical routing indices from the previous step to pre-assign slots before the forward pass. Experts see stable, predictable demand, oscillation eliminated. Second, SWE-glue clamping. Early in training with random weights, SWE-glue gate values can explode, causing loss spikes. Hard clamping gates to -10 to +10 catches pathological values. At those extremes, SWE-glue is already saturated, so clamping has zero effect on a well-trained model, but reliably suppresses explosions during the critical early phase. Together, these 2 techniques made 32 trillion tokens at 1 million context stable. Post-training runs in 2 stages. Stage 1 is specialist training. For each domain, math, coding, science, reasoning, writing, tool use, and safety. A dedicated SFT run followed by GRPO reinforcement learning with domain-specific correctness signals. Unit test pass rates for code, proof verification for math. Each specialist outperforms a general model in its domain. Stage 2 is on-policy distillation. Unlike standard distillation on pre-generated outputs, OPD generates student responses online during training, then minimizes reverse KL divergence against 10 or more teacher models using full vocabulary logits, all 100,000 plus tokens at each step, not just the top K. Reverse KL produces mode-seeking behavior, sharp, confident outputs. The result is dense per-token supervision from every specialist simultaneously, outperforming pure reinforcement learning. The results are clear. Codeforces, 3,206. Legendary Grandmaster, highest ever by an AI. Putnam 2024, to 120 out of 120, a perfect score. SWE-bench verified, 80.6%, correctly resolving 4 out of 5 real GitHub issues. MRCR at 1 million tokens, 91% on multi-document retrieval. The big picture. CSA and HCA make million token inference practical at 7 to 27% of prior cost. MHC, muon, anticipatory routing, and SWE clamping together enable stable training at 32 trillion tokens. On-policy distillation absorbs the expertise of every domain specialist simultaneously. And both models are released with open weights. Million token frontier intelligence is now available to the entire research community.